Hi, I am Weiss from the Technion, and I'll be presenting the paper Extracting Common Components from Partially Observed Views Using Diffusion Geometry. This work was done in collaboration with Professor Hau-Tieng from NYU and Professor Talmon from the Technion. Multiview data refers to data acquired from multiple sensors or modalities, and is common in many applications such as ECG, autonomous driving, and wearable medical devices. In many applications, we're interested in some common component between the views, such as the heart rate, common objects, or patient condition that are reflected by the different views. We discussed the setting of n measurement pairs from two views. Most existing methods assume that the views are fully aligned, which means, as in the illustration here, that for each measurement from the first view, there is a corresponding measurement from the second view. In practice, measurements are often missing due to poor data quality, expensive or irrelevant measurements, or patient dropout. Our focus is on relaxing this alignment assumption, requiring a smaller subset of m-aligned measurements, and allowing for additional n-m measurements only from the first view. The common components are extracted by mapping each sample pair to a single low-dimensional embedding, representing the common components. We take a manifold learning approach to this problem, where the data is assumed to lie on a low-dimensional manifold, which we approximate with a discrete graph, as is seen in the image. This is done using feature affinities as graph weights, using the Gaussian kernel. The geometric structure of the manifold can be extracted from this graph, for example by using the diffusion maps algorithm. We normalize the kernel K to make it column stochastic, and thus it defines the transition probabilities of a diffusion process on the data manifold. Consider some initial distribution f null, then the matrix Q describes its progression in time. Observe this dumbbell-shaped dataset on the right side. We can see that the mass propagates to the right side fast, and then slowly to the left side, reflecting the weaker connectivity to this left part. I hope that at least intuitively, this convinces that the diffusion process recovers the geometry and connectivity of the data. It can be shown that the left eigenvalues and eigenvectors of Q reflect this propagation structure. Next, we discuss the Alternating Diffusion Maps algorithm for extracting common components from aligned multiview data, which is the basis to our work. First, construct Q1 and Q2 for each view exactly like before, and observe their product QADM, which describes an alternating diffusion process. This diffusion process is illustrated with these two manifolds with discrete data samples denoted by triangles. We illustrate the alignment by coloring samples such that samples with the same color are considered aligned and the mass at aligned points is equal. Consider QADM as a diffusion process split into two steps, Q1 and Q2. First, Q2 propagates mass according to the geometry of the manifold M2. Then, the mass is transferred to the first manifold through the alignment, and the mass is propagated through Q1. Intuitively, this operation filters out view-specific components, as Q1, for example, is unaware of the components specific to the second view, and therefore they are filtered out by it. Similarly, Q2 filters out the first view's specific components, thus extracting common components overall. As in diffusion maps, the eigenvalues and eigenvectors can be used to extract the common component geometry. However, since QADM is not guaranteed to have real eigenvalue decomposition, the SVD is often used instead. ADM has been used in many applications, however, it is limited as it assumes fully aligned views. Now, to introduce our method, we define two kernels. First, the m by m kernel, K2 tilde, which measures the affinities between the second view samples. As in ADM, we column normalize it to get Q2 tilde. Next, define the n by m kernel, K1 plus, which measures the affinity between the aligned samples and all samples, and column normalize it as well to get Q1 plus. We then define the symmetric n by n diffusion operator, S by the gram form of Q1 plus Q2 tilde. This includes the transpose operators P1 minus and P2 tilde, which are called backward diffusion operators, which were shown to capture geometric structure in both single and multiview settings. Here we present the underlying diffusion process, which alternates between views and the partial and aligned samples. Triangles denote aligned measurements, and circles partially viewed samples from the first view. Recall that there is alignment between the triangles, through which mass is transferred between the manifold. We will not use colors to represent this alignment further, as we reserve colors for another purpose. Now observe how S operates on a function f on the data points by splitting it into 4 steps. First, the mass is pushed or propagated from all samples to only aligned samples by P1 minus, taking a long vector in Rn and returning a short vector in Rm. Then, through alignment, mass is transferred to the second manifold and is propagated by P2 tilde and Q2 tilde. And finally, the mass is pushed back to all points by Q1 plus, returning a vector in Rn, resulting in a diffusion process that incorporates both views and all the available measurements. This is in contrast to existing methods that embed the aligned samples first, and then later add partial samples by interpolation in the embedding space. Overall, we get a process that is conceptually similar to ADM, but with the incorporation of partial view samples. Then the embedding is given by the eigenvalue decomposition of S, which is equivalent to the SVD of Q1 plus Q2 tilde, up to squaring of the singular values. We term this algorithm ADM plus, as it degenerates back to exactly to ADM when all samples are aligned, thus acting as a natural extension for partial alignment. ADM plus has time complexity O of n times m squared and memory requirements of O of n times m, improving upon O of n cubed and O of n squared for ADM respectively. To illustrate our algorithm's performance, consider a toy problem of 3 characters rotating at different rates, which we observe through 2 views, each capturing 1 common character and 1 view specific. We are given 50 aligned measurement pairs and 950 additional images only from the first view, from which we extract the common component, which is the rotation angle of the common character. Therefore, we embed the common component to dimension 2, which should give a circular embedding. Here we see the resulting embedding from different methods. For ADM with 1000 aligned samples, we see a clean and thin circle, indicating that the view-specific components were filtered out well. From the interpolation baseline, we see that the circle is much thicker and noisy due to view-specific components. ADM Plus showed these artifacts too, but to a lesser extent, indicating that the view-specific components were filtered out better by our method. In our theoretical analysis, we present the asymptotic expansion of the operator S and discuss its interpretation. Specifically, we show that it multiplies the diffusion by a density ratio of the aligned and full data, which helps guide the diffusion to reduce the impact of discrepancies between these distributions. We further show empirically that this theoretical result translates into practice to finite samples, as here the error of the angle estimation of ADM plus is the least affected from distributional discrepancy controlled by the parameter gamma. We apply our algorithm to other domains. Here we show that we are able to recover coherent sets in dynamical systems. We consider the sets recovered by ADM plus are similar to ADM and are more consistent in time compared to the baselines below. We also apply ADM plus to a classification task in fMRI and show that the dependence on the fraction of aligned samples. We see that the ADM plus performs better than competing methods, especially when there are few aligned samples. As the number of aligned samples increase, we see that ADM plus approaches the performance of ADM as expected. To summarize, we introduced a novel multiview manifold learning algorithm for extracting common components with partial alignment. Our approach is novel and doesn't require imputation or interpolation. We present theoretical analysis and experiments across 3 different data domains. Thank you for listening. We look forward to see further research and work related to this work and hope you find it interesting.